Yes. South, somehow close to Normandy, from which we came.
It's Bretagne.
Bretagne.
Grande Bretagne.
Yeah,
Small
but
one.
still closer to Normandy than anyhow. Yes, Arnaud Debussche will speak about the nonlinear Schridinger equation with noise, wide noise dispersion. Welcome.
Okay, so first, I apologize for those who were attending the January conference because Anne Debussche gave almost the same talk. But hopefully, excuse me?
We use the same slide.
No, unless she used mine, because but she doesn't like my slides in general, so so it's different. But hopefully the last 3 slides will be new because it's a new result which I finished this week. So okay, so no, yeah. Okay, so this is the starting point of our work. So it's a motivation that comes from engineering, in fact. So it's from optical fibers. So what engineers try to do when they build very, very long fibers to propagate signal. So in fiber, you have 2 effects in fibers. You have the linear effect here, which is the Laplace term. So because of the I here, it's not like the heat equation. This is a unitary thing. No smoothing, nothing, but it's what happens in a fiber, and you have the nonlinear effect of the fiber. And the linear part is responsible for the so-called dispersion. Dispersion means that when you have a signal, very localized in space signal, it has tendency to delocalize. So this is not a good thing when you try to propagate a signal. So what engineers try to do is to have a 0 dispersion, but this is not possible in practice. So they alternate between positive, negative with small amplitude dispersion. And what you get at the end is a small parameter, something which varies. Oh, sorry, I forgot to say that in a fiber, this is the equation, but the time should be thought as the distance, okay? The time is when you have a long fiber.
Fiber is a cable, or what would
it's an optical fiber, so it's a line. So it goes from England to United States, okay? And this is time. The time is the distance. In fact, the real equation should be EI du over dz, if you have z here, plus epsilon m of t, d2u over dt squared. So for obvious mathematical reason, we switch notations, okay? So in fact, the mathematical time is the physical space, okay? So this is why the dispersion varies along the fiber. It depends only on time and not on space because it doesn't vary in time. And then there you have small residual nonlinear effect. And to get something, which is a common argument in physics, just to get something, the only power you need is squared here. Otherwise, you just don't see anything anymore, okay? Okay, so of course, if you let epsilon go to 0, in this form, you don't see anything. You just see that the epsilon is constant. So it means that you have missed the effect. So you rescale and get this. Okay, so this is the rescaled equation. And then if m is a random, which is stationary, it's natural to expect that it's stationary. The characteristic of the fiber doesn't depend where you are. So you expect that this goes to white noise. Okay, so this is the limiting equation. Okay, so the formal limit is very classical. Okay.
So what is x now? You
said
x that.
Oh, sorry.
Time is the distance.
X is the physical time. Okay, this is the true equation. So I change notation. Z is time. And t is x.
There's no boundary condition, I mean, because the time is negative now.
Well, no, because in fact you send the signal at the starting point here, and you suppose you know the whole history of the signal. So it's no problem of boundary condition. You really send the signal at z equals 0. Okay, and you suppose you know the whole signal, so from t negative to t positive. So this is a well-set thing. Okay, so the aim of our work was to understand this equation and to try to justify the limiting procedure. Okay, so at first point I want to mention is that apparently there is a single Brownian motion in this equation. So you think, okay, this is 1D, it's nothing because you just use Sussman's idea. And we'll see that's completely different because we cannot solve this equation here. Okay, so we cannot just use Sussman's idea.
The norm is means Stratonovich.
This is Stratonovich noise, of course, because when you pass to the limit here, you get a Stratonovich noise. Okay. Okay, so we just, since we are mathematicians, we generalize the equation. So we go to any dimension, although the model is only 1D. You don't have d-dimensional time, of course. And we generalize the nonlinear power to cubic to any power. Okay. And so both for the limiting equation and for the original equation. Okay, and what we want to do is to study both equations. So this work was motivated by work by Renaud Marty, who did in physics. In his thesis, he studied exactly this problem, but there he replaced the nonlinear term by a very nice Lipschitz bonding blah 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 term, in which case you can do those Sussman arguments. So it's completely different. So here we cannot do this. Okay, so in order to understand this, we still interpret this as a linear equation perturbed by a nonlinear thing. So we still want to do this as a semilinear equation, okay? As if this part was deterministic. So we need to understand the linear part of the equation, okay? So this is non-autonomous now because there is d beta here. So it's a propagator. It's not it's a semi-group. So and you just use the mind form here, and you try to understand if you can do a fixed point of this equation. Okay. So to understand what the basic idea is, we go back to the deterministic equation. Okay. So you just forget about beta dot here. You put 1. So you do the same thing. Now the linear group here is just exponential IT delta. You write the mild equation, and that's what you get. Of course, this is I delta, so this is an isometry in any Sobolev space, any L2-based Sobolev space. So you cannot work in L2-based Sobolev space to have ultra contractivity here. So you need something, if you want to do a fixed point, to tell you that if this is in LP, then when you apply this operator, it's better. Okay? You need the ultra contractivity argument to do a fixed point. Otherwise, you're just dead. Because if you start from LP, you go into P over 2 sigma plus 1 here, and it doesn't work. Okay, and this is exactly what the Strickart estimates are. So this transposition is rather messy. I'm sorry, but the idea is very simple. Okay, so well, I will explain where they come from later. But this is exactly the content of the Strickart estimates. You see, if you start from f in L, P and P prime are conjugate exponents. This is like this. F in LP prime, for instance, think about L1. Then you apply this operator and gets to LP for L infinity. For instance, or if you go from L4 third, for instance, you go to L4. Okay, so you have this extra integrability due to the action of this operator here. Okay, and so with this you just do a fixed point argument. So I wrote exactly the argument. For instance, if you take P prime, P equals 2 sigma plus 2, which is written here. So P prime, as written on the blackboard, is 2 sigma plus 2 over 2 sigma plus 1. So when you apply, here, or there should be a sigma here. So when you do U 2 sigma plus 1 in LP prime, this is just U in LP to a 2 sigma plus 2. So you can iterate your argument, okay? You have a way to go from one space to itself, which is LP. And then you have the integration in time. And in fact, you see that you need that 2 sigma plus 1. You'll have a condition that 2 sigma plus 1 R prime should be less than R. Because you also need this in space. And this is exactly the condition that appears when here, to solve the equation. Okay? So this is the deterministic argument. If you have questions, please, because I know I'm quite fast. Okay, so now I want to do the similar thing on the stochastic equation. So first I write down the explicit solution of the linear equation. Okay? This is Stratonovich. Okay, just do standard calculus and you can write the solution using Fourier transform, and this is it. Okay, so again, since this is unitary, it's a modulus 1, you see that you have a unitary transformation in any Sobolev space. This is very standard. But if you go back to the original phase space, you get this explicit formula for the linear equation. And there you see how you can prove such inequalities. Here. And you see why maybe you have some hope to do the stochastic case. Because here, if you just take the modulus ut, there should be an x here, I'm sorry, again. There should be, of course, an x, so v of t and x. You just mount by this. And here, you just bound by VL1 norm of Vs. Okay? So again, you have the property that if the initial data is in L1, then the solution is in infinity. Okay? Of course, you have to pay the price. Okay? And in fact, this is exactly the same as for the deterministic equation. What you get is ut u0 less than 1 over t to a d over 2 u0. So it's exactly the same thing, but you have replaced t by beta t. Okay? And there you see, oh, maybe there is something very good here, because this is a very formal argument, but beta t is like square root of t. Okay? So it means that you lose less power of integrability in the stochastic case than in the deterministic case. But the main problem is that when you try to compute the expectation of beta t to a negative power, you indeed have that this is t to the minus alpha over 2, but alpha is strictly less than 1.
On the left-hand side, you have Vt. There is no S.
Yes, I'm sorry. I thought I corrected all my mistakes, and there are still many mistakes. This should be VTSX. Okay. In fact, Vt is written here. Okay, but this should be Vt starting at S at point X. Okay. This is here. Okay. So you see that you may hope to derive. Okay. So this is the starting point. Then you write this. So this is L infinity. This is equal to norm. And then you just do some interpolation. You go from LP prime to LP by interpolation. That's it. And so you can repeat this argument because you have isometry in L2. You have dispersion from L1 to L infinity. So you do an interpolation argument and you have this dispersion inequality. Okay, you go from LP prime to LP, but you pay the price of this thing. Okay? So we need something like this. Remember, this is the Strickhardt inequality. In the deterministic case, again, the proof is not, it's quite easy. Because when you interpolate those two inequalities, you get that u t minus s f of s in LP prime is less than a constant t minus s to the minus d 1/2 minus 1 over p f of s in LP. Okay, so when you integrate this, so when you integrate this in time, and this is a convolution. Okay, you have a convolution between f and t. Okay, so you can use convolution inequalities to see that it is in LR, and this gives you exactly the result. Okay, and fortunately in the deterministic case you have Hardy-Littlewood-Sobolev inequality. No, I don't know the name. Remember the name, but you can do as if t was in L, t minus 1 was in L1. Okay, you can do this.
But it's
Young inequality, but really critical case, so it's not Young anymore. It's okay. Yes?
No.
Yeah, okay. But here we cannot do this because it's not a convolution. In average, it's a convolution, but if you first average, you lose everything. So you need a convolution inequality, and we were stuck at that point for a long time until we get a convolution inequality. Okay, and this is a elementary result, but which was quite hard to derive, which is essentially the basic of the convolution inequality. When you do almost a convolution between beta t, it's a beta convolution, if you wish. And this gives you this. So that you see that I lose something. Because if this was t minus s, I would have, here I could put LP with alpha plus 1 over p equals 1 plus 1/2. Okay, so p would be bigger than 2, since alpha is strictly less than 1. So I lose something. Because alpha less than 1 and p equals 2. Okay. If someone has any idea to improve this, I buy it. Okay, so then, starting from this, you interpolate exactly as the same proof as convolution inequalities, the basic one, not the critical one, and you get this. And this is exactly the argument you need to go from the equivalent of a stochastic form of this to the Strickland inequalities. Okay, so you do the same argument as there, and you get the result. Okay. So this is with the precise details. So if you take P and R, but you need them to satisfy some condition, of course, because this exponent is linked, of course, to this one. Then you go, but of course you integrate, but you integrate afterwards. That's the whole problem. In fact, if you were able to work with LR in time, L rho in omega, LP in space, that would be very easy, but you cannot do the fixed point with this. So when you look at this result compared to the standard deterministic Strickland estimate, you lose something because in the deterministic case you have equality here, and the loss is in my convolution inequality. So you lose this, but you gain something here, because in the deterministic case, beta here is 0. Okay. So you see that when you do a contraction argument, you always have the time, which gives you the smallness, so that you have a contraction. Okay. So in the deterministic case, beta equals 0, and you'll get the contraction thanks to R prime when you go from when you do the fixed point in time. But here we have something better. Okay, and then since you want to do a fixed point on this equation, where is it? Here? No, it's before. Yes, here. So you also want this term to be in the right space. Okay, I have only worked on the first term here, but I need to work on this one also. But this is rather standard, but not so much. Okay.
Excuse me. Are you able eventually to replace your beta by a Hölder continuous function?
We'll talk about that later. Otherwise, I could do dos Sussman.
No, but with not without dos Sussman.
You'll see. You'll see. Okay, so and the free term, as we usually call it, is treated here, and this proposition here tells you that if you start from L2, but this does not depend on time. This is the initial data. You go to the right space, and this is done by it's a very, very common argument in the deterministic theory. It's a duality argument, but you have to be very careful in the stochastic case, because here I'm working only here. This result is true only for f which are predictable. And when I do the duality here, if I do it naively, it doesn't work at all, because I'm working the dual. The basic argument here is that if you take u0 against a function ft and integrate from 0 to t and take L2 product in x, this is the integral from 0 to t of u0, u minus t, ft, yes, dt. So this is u0, integral from 0 to t, u minus t, ft, dt. Okay, so it means that the dual of the operator which takes the initial data is almost the operator I'm working on for the Strickhouse estimate. Okay, but this is not true in the stochastic case, because here in the stochastic case, your test functions are only f0 measurable. So you get the projection, you get the conditional expectation on f0, so you cannot do anything with this argument. So you have to be very careful. But you can work anyway. But this is a very bad thing, because we could do a lot of things with this argument. But anyway, it works here. Okay, so then we need to solve the equation. So as usual, we need to do some truncation because of the power here. So we truncate, and it's very natural to truncate in the norm I'm doing the fixed point. And it's very, very standard now. You just do the fixed point with exactly as in deterministic theory, and you get a solution, a global solution of the equation. Oops. Yeah. So a global solution, and since the equation, the original equation conserves the L2 norm, it's very natural that you still conserve the L2 norm. But of course, this is a truncated equation, so we need an estimate in the truncation norm to get global solution. And this is also, again, not a so obvious step. So we defined the stopping time when, as usual, when the truncation starts to act. And the only thing we can say is that if the time is not too big, then the probability that the lifetime is smaller than if it's small time is not zero. That's the only thing we can say. Okay? We cannot say that it's global. We just can say that if t is not yes, because this exponent is positive here. So if t is small, so you choose r such that this is less than 1, the probability that tau r is bigger than t is positive. This is the only thing you can say. I'm not able to do any better. And to get this, you just work on the equation, and well, I skip. It's too late to do computation. So you just do, this is fairly inequalities from Markov inequality. So this is far from giving global existence. Okay. But the argument, I've never seen this argument, but it's not very surprising. It's quite a common argument. I've always known that this argument can work, but I don't know any equation where you can do it. So what you do, you restart at the time when the truncation starts to act. Okay? And what saves you is that the truncation, when you restart with the truncation it will be the integral starting from the new time. So it starts at 0. That's a good thing. Truncation restarts at 1 because this is 0. So you have a solution on another time. Okay? And so for this solution, you have the same estimate. And what saves you is that this estimate depends on the L2 solution, which is conserved. Okay? So then you can iterate the argument. Of course, so you choose a very small t, and you iterate the argument. So you have a solution on random times. They are very small, but they cannot be always small, because conditional to the past, they are not all small. So then it's just a standard argument using conditional expectation. The probability that they are all small is 0. So the limit of the sum has to be the infinity, and you have a global solution. So in fact, at the end, you have a global solution without any estimates. I only know that it's in LP, LR, LP almost surely, but I have no estimate on the moments at all. Okay. So we have a global solution. So I've been a little fast because I've skipped details, so please don't hesitate to interrupt me. But I think it's late and you don't want to hear too.
So it is a method to prove that there are no explosions?
Yes, yes. But it's very particular because it works for two reasons. one reason is that the truncation, when you restart, it vanishes, because you see it, when you restart at t equals to r, this is 0. If I do a truncation in an infinite time, this is not true, of course. Okay? And the second reason is that this estimate depends only on the L2 norm, which is conserved. Okay? So I got the result. So since I've lost on the convolution inequality, but I've gained on the power of t, I'm able to go exactly to the same limit as a deterministic case. Okay? This is exactly the same limiting exponent as in the deterministic case. We get a global solution. And moreover, this is then very standard. You have preservation of smoothness. Okay? So what about the limit epsilon go to 0? I thought I did correct this. Okay, yes, on the next slide. Okay, so now I take this here. So here f is a general function, but it should be u to the 2 sigma. But here I take a C2 bounded with bounded derivative. In this case, it's very, very easy to solve the equation. Because you use, in this case, you use just this mind form. And you do a fixed point in H1, which is an algebra in dimension 1. Okay? And you just do this. This is nothing to do. So in this case, the equation is well posed. So to answer your question, Francesco, it's well posed even for n continuous. Because you can write down explicitly. So here, okay, it's the case with n. Because here, Sn, you write it down explicitly in terms of n and not in terms of its derivative. So it's well posed for continuous n. Okay. And in fact, you have continuity with respect to n. This is very easy. This is what Marty did. Well, no, it's not very easy. This is what Marty did in his thesis, but he's not a PDE guy, so. But it's elementary PDE argument, okay? And so then you know that when epsilon, so this is what appears in the original argument. So when epsilon goes to 0, you know that this goes to a Brownian motion. This is well known under a classical mixing condition on the random coefficient. So you just take the limit into the equation. You take an epsilon dot going to beta dot, and that's it. So you have convergence in distribution of u epsilon to the solution. Okay, but this is true only when f is a nice C2 bounded function. Okay, so in this case, you get the solution of the stochastic equation from the solution of the deterministic equation. Okay. In our case, it doesn't work, because if you replace f here by the power, then I don't know if there is a solution, because I cannot do this argument. I have only local solutions. Okay. So what we do is we do well, it's rather standard. So we do a cutoff, because we don't know if you don't have the cutoff here, we don't know if we have a solution, because we don't have Strickard's estimates with time varying coefficients. Okay, I just proved one with the white noise, but it is because it's the white noise. When it's a random process of this type, I don't have a solution. So I have only a local solution. So I introduce a cutoff equation, so that I can use Marty's method and prove that this converges to this when epsilon goes to 0. Okay, so this is okay. So because also of this argument, because I have a solution in I have convergence in HS for s bigger than 1/2. Remember this here. This is in HS. Okay, but in dimension 1, s bigger than 1/2, you get an infinity. So you can get rid of the truncation in an infinity now. This is not the same truncation as before. Okay. So what I get at the end, well, then you use the standard argument, which tells you that in fact the solution of this equation, of the original equation, well, of this equation remains bounded on longer and longer and longer time. So in fact, you have a solution of this equation. Maybe I should write down the details. So if you take the original equation, this is written in terms of the original equation. So the solution here, so you have u epsilon m will be less than n on a time tau epsilon which does not depend on m, and the probability that tau epsilon is bigger than t goes to 1. So that the solution of this equation gives you a solution of this equation on longer and longer time. So it's a completely different situation compared to Marty's method. The solution of a stochastic equation gives you the solution of a deterministic equation. Okay? Because you know that you have a limit for when epsilon goes to 0. Okay? You don't get existence from the deterministic or the stochastic from the deterministic, but exactly the converse. Okay? So it's really not a Sussman argument. Okay. Okay, so you get the result. So, well, I have plenty of time to do this new result. So this is a very new result I've done with Yoshio Tsutsumi when he was in Rennes 2 weeks ago. The starting point is this estimate here. This is a very nice estimate in the deterministic case. So in fact, you have some smoothing. So the Schridinger, recall that the Schridinger equation, U capital T, is exponential T delta. Okay? So it doesn't smooth, apparently, when you're in L2 spaces. But if you do this strange thing, you first take the square and then take a derivative, then it's still in L2. Okay? So you have some smoothing in a sense. Okay? And the proof of this is, well, the proof of this is quite technical, but there is another smoothing effect which is very easy to see. It uses just the Fourier. Or if you have another smoothing effect which is due to Jean-Claude Sau and Peter Constantin. So you write this, you look at this at x fixed, and you take the square. So if you integrate in space, you are doing the L2 norm, so you just lose it because you don't have smoothing effect in the L2 base space. But so the idea is first to integrate in time. Okay, and if you do this, so you write you write this in Fourier transform. So this is exactly this action on U0 hat of xi. And of course you have your D1 half here, which gives you a xi. And you take the square and dt. Yes. Sorry. I'm sorry, I've done something bad. Yes, there is an integral xi, of course. Big xi, and the modulus is here. Sorry. Okay, this is the true solution. And then it's a very nice idea. You do some change of variable here. You cannot do it, but you can in fact. You write eta equal xi squared, and you interpret this as a Fourier in time, not Fourier in space. And in the two change of variables, the xi disappears. Okay, so this is the smoothing estimate. So you see that you do have some smoothing effect, but you have to first do some average. Okay, in this estimate, the average is in time. Okay, and you can improve this. This is Ozawa and Tsutsumi. If you first take the square and you repeat essentially the same argument. So you have some smoothing, but if you do some average first. Okay, and this is for, of course, it is, well, this is rather different. So we said, okay, and what is the point of this inequality here is that in dimension 1, what does it tell you? It tells you that if U0 is in L2, this squared is in almost H1 half, and H1 half is almost L infinity. Okay? And this will be L4 in time. So you almost, so this gives you an estimate L4 in time with respect in H1 half in X, which is almost with L4 in time and infinity in X. And this is the Strickart estimate. This is exactly the Strickart estimate in dimension 1, the best Strickart estimate. But the hope here is that the proof is completely different. And I don't have a convolution anymore. Okay? So we thought, okay, let's try to do this again, this in the stochastic case. And it works. But the proof is completely different. And the proof, it's based on, it's long to write, but I like to write it because it shows something very, I think, important for the equation. Maybe I should take my notes because it's not that easy to do. So
in dimension greater than 1, there are some known effect like this one.
yeah, but they are not as good. They are not as good as this effect. You lose a lot. So this is only in dimension 1 it works, unfortunately. Okay, so what you do to prove this estimate, so you write the Fourier transform of this squared, so this is S, sorry. Okay, apply to side, and you square it. So you imagine that the quantity is quite horrible. But this is why we needed 2 weeks to find it, just because I didn't want to do this computation because it's too horrible. But what you get is the integral from 0 to t. So the square, this is a convolution. So here you get I beta t minus beta s psi squared f hat of s and psi. And so, okay, sorry, it's a convolution, so it's psi 1 squared psi minus psi 1 squared minus psi 1 squared f of s and psi 1 f of s and psi minus psi 1. Okay, d psi 1, then ds, and then you square. Okay, sorry, there is another mistake. Sorry, the square is here. So in fact, I have a double integral here, and here it's beta is 1, and here beta is 2, and see here it's at 2 different times. And you square, so you get a quadruple integral in time, and you get 2 integrals in, so this is of 0t to the 4. So I'm sorry for this very technical thing, but I will get to the point I want to show you in a moment. And when you do all the computation here, what you get is exponential I, beta t minus beta s1. So this, psi minus psi 1 squared minus beta s2 psi 1 squared plus minus I beta t minus beta s3 psi minus psi 2 squared plus beta s4 psi 2 squared, and all the product of f here, okay, and all the d's. And then you take the expectation. Okay, because here the averaging effect from here I will get it from the expectation, not from the integral in time. Okay? When you take the expectation here, you say, okay, but this is a real mess because I have all these quantities here. So this is at S1, the other one is at S2, blah, blah, and so on. But what you do is, of course, you know that you have independencies here, okay? Oh, sorry, no, this is beta t minus beta S2, and beta t minus beta S4 here. So what you do, you just say, okay, which one's the biggest? So for instance, you have four possibilities, S1, S2, or S3, or S4 is the biggest. So let's, for instance, imagine that S1 is the biggest one. What you get is this quantity at the end. So you take all the sum, because here, of course, you write that this is beta t minus beta S1 plus beta S1 minus beta S2. And so you have cancellations, and you get 2 xi1 minus xi2 times in terms of time less than S1, fs1, fs2, fs3, fs4. So then you take the expectation, okay? And here you have a smoothing effect because you use that the expectation exponential I beta t minus beta s xi, just write this is xi, this is expectation, or minus t minus s over 2 xi squared, okay? So this is, so you see a smoothing here, okay? So you'll have xi squared, xi minus xi squared 2 squared, and this xi squared will kill, of course, I've forgotten here, this is the d1 half, this xi here, okay? And this is how you get the smoothing effect. So it's completely different proof compared to the deterministic case. And what's hidden behind this proof is just, so what I said to Franco was not exactly true, is that when you write, so this is Stratonovich, when you write the equivalent Ito form, you get so it should be a plus. You get to 4th power here. Okay, so it's a way to use this Laplace operator. Okay, and so using this argument, I can prove this estimate. Oops, and then so I have those two estimates. Then it's just standard game for when you work on this equation. So you go from L1 L2 to this, L1 L2 to L1. You use Gargli and Dierenberg, and tells you that you go from L1, L2 to L5, L10. Sorry, this should be L10. Okay, so L5, L10, L1, L2, it means that you can multiply 2 by 5. You go to 10. It means that you can solve the quintic Schrödinger equation in 1D, okay, using exactly the same method as I've done before. So you can solve the quintic equation in L1, L5, L10. Sorry again for this problem here. It's L5, L10. So you have a good solution of this equation. And it's well known that for the deterministic equation, okay, for this deterministic equation, if the initial data is small, you have global existence. And you get there exists initial data which blows up in a final time. Okay. So this is the stochastic equation is better well posed than the deterministic case. Okay, so you have a better estimate. And in fact, this is not surprising at all because there is. So I have still 15 minutes. I've been very fast. Sorry, but I think that this result is not optimal for one reason. If you take the deterministic equation, okay, and you try to see if there is a scaling, if the equation is scaling invariant. So you take, you look at u lambda, and try to see when this is also a solution of the equation, okay? And of course, here, because of the relation, one time derivative, two space derivatives, so this has to be 2, okay? And when you plug this in the equation, you find that, I don't remember, alpha plus 2 equals you need that 2 sigma plus 1 alpha equals alpha plus 2. Okay, so which means that alpha equals 1 over sigma. Okay, so the equation is scaling invariant with this scaling. But then what if you compute the L2 norm of u lambda? Okay, and you just do a change of variable, and what you get is lambda 2 alpha minus d, the L2 norm of u at lambda squared t. L2, sorry. So it means that if the equation is well posed for small initial data, and if this is positive, okay, you take lambda large, lambda small, sorry, and you get an equation well posed for big initial data. Okay, so it means that if 2 alpha is less than d, small initial data can be brought to big initial data. Well, big initial data can be brought to small initial data by the scale. Okay, so this is subcritical. This is a very standard PD argument to see the critical exponent. And this argument is just sigma strictly less, oh sorry, there's no problem with my signs. It should be sigma strictly less than 2 over d, okay? If you do the computation right, okay? So this is why you get 2 over d, and this is why it's completely optimal. And this is why when sigma equals 2 over d, this is the critical case. And in this case, it's possible to have global solution for small initial data and non-global solution for large initial data, which is not possible in this case. Okay? Now, if you work on the stochastic equation, the scaling is completely different in this case because you have the white noise. So when you do a scaling invariant thing, the beta is not 2 anymore. You need to take beta equals 4. Okay, so the scaling is completely changed. And when you do the same argument as here, you see that the condition is sigma strictly less than 4 over d. So you should be able to go to twice the power as in the deterministic case, which I'm completely unable to do now. I'm able to go to the critical deterministic case. Okay. So that is hopefully a work in progress. Thank you for your attention.
Questions and comments?
You don't have to.
Okay, thank you very much for this very interesting talk.